Hi everybody, this is Dr. Nigra with the Chem Calculations Screencast. This one's going to be looking at the reaction quotient, which is part of our unit on equilibrium. All right, the reaction quotient is represented by a capital letter Q. All right, so when we talk about equilibrium and then non-equilibrium conditions, we're either talking about KEQ or Q. All right, Q specifically is the ratio of products versus reactants at any time other than equilibrium. All right, so if you're at equilibrium, then this ratio of products to reactants is called KEQ. If you are not at equilibrium, then we call it the reaction quotient. All right, and we can use this for a couple different things. All right, we can use it to determine if we are at equilibrium. If you know the KEQ value for a particular system at a particular temperature, and then you calculate this ratio of products to reactants under a given set of concentration values and compare the two, if they're equal, you're at equilibrium. If they're not, then you're not. That easy. All right. Now, once you make that determination, if you're not at equilibrium, then we can compare Q to KEQ and determine which way we're going, which way reaction is progressing. All right, now what does that really mean? All right, we know that as the reaction first begins, we have a lot of reactants. So we're going to see that rate of reactant to product start to drop, all right, as we start to use up more and more of those, and the concentration of products will start to grow. All right. After some time, the amount of products start to grow enough that they can collide, successfully react. And so we see the rate of the reverse reaction start to increase. And then we see the rates of the reactants start to adjust. All right. So by comparing the ratio of the reactants to products under a given set of conditions to what it should be at equilibrium, we can decide if we still need to produce more products or do we need to go back and produce more reactants. All right. When we calculate Q, we need to write the Q expression, which is exactly the same thing as what we see with KEQ. It's a ratio of the products versus the reactants. All right, and the same rules apply that we saw before. So gases and solutions only. Coefficients equal exponents. And just like we saw with KEQ, it is temperature dependent. All right. Now, when I think about this comparison of Q and KEQ, I think about it like this. All right. On one side, I have my reactants. On the other side, I have my products. And somewhere in between is the ratio, which is KEQ. All right. For a given problem, I'll plug in my amounts that are given for my different reaction components into my my Q expression. And then I'm going to compare. I'm going to say, well, where does Q fall on this number line? Let's say Q for a particular situation is down here. All right, so that means that Q is less than KEQ. So I need Q to increase to reach equilibrium. I need that Q value, that ratio, to get bigger. All right, if that's the case, then I need to increase the amount of products. So more products will be produced, all right, because that will increase the numerator of my ratio, which will make my overall value get larger. All right, now I could have a different situation. Let's say instead Q is up here. All right, so in this case, Q is greater than KEQ. All right, if that's the case, then I need my Q value to be smaller so that it can match KEQ, which means I need my denominator to get bigger. All right, so I'm going to see the reaction progress towards the reactant side. So more reactants will be produced. All right, and then finally, under not rare occasions, in some cases you will be doing your calculations and you'll find that the two are equal to each other. Q equals KEQ. If that's the case, then you are at equilibrium. All right, so Q is a handy way to know where you are in terms of reaching equilibrium. Do you need to make more products? Do you need to make more reactants? Or are you at equilibrium? And we determine that through our comparison with KEQ. All right, so let's scroll down. We're going to actually do a little bit of practice writing some Q expressions. This shouldn't be anything new from what we did for KEQ. We're just going to write Q. All right, still products over reactants. So we check, we've got gases, gases, gases. 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. So everything's balanced. We start with our products. NH3, it has a coefficient of 2, so we're going to square it over our reactants. N2 times H2. Now H2 has a coefficient of 3, so we're going to cube that one. So this is our Q expression for this particular reaction. All right, we go below. Q again, we check, we've got a gas, and a gas, so that's all good. Check our balancing. We've got 2 nitrogens. Oh, no, this one is not balanced. We got to fix this one. All right, so we have 2 nitrogens, 3 nitrogens, so we're going to need 3 of these, which is going to give me 3 oxygens. Here's 1, and here's 2 more, so now it's balanced. All right, so we start with our products, N2O. Whoops, left out the O. All right, it has a coefficient of 1, so we leave it. NO2 has a coefficient of 1, so we leave it. Over our reactant, which is NO gas, has a coefficient of 3, so we cube it. All right, so that would be our Q expression for this reaction. All right, now we move over here. All right, check our reaction. Oh, here we have a solid, so that's not going to be in our reaction. Right, we then look on the product side, we've got a gas and a gas, so that's fine. Check our balancing, 4 nitrogens, 10 oxygens, 8 plus 2 is 10. All right, so we start with one product, NO2, coefficient of 4, so we take it to the 4th power, times O2, no coefficient, so we leave it as 1. So that would be the Q expression for this reaction. And then we end with this last one. All right, if we look, we've got Q equals, all right, solid, so that one's going to go. Solid, so that one's going to go. So we only really have one thing that could go into our expression. But we should check for balancing. Calcium, 1 carbon, 1 carbon, 3 oxygens, 3 oxygens. And then our Q expression is just the concentration of CO2. All right? So again, exactly like what we do for KEQ. All right, now let's try a problem. For the reaction of N2O4 gas reversibly producing NO2 gas, the KEQ is 0.21 at 100 degrees Celsius. At a point during the reaction, the concentration of N2O4 is 0.12 molar and the concentration of NO2 is 0.55 molar. Is the reaction at equilibrium? If not, in which direction is it progressing? All right, so this question, is the reaction at equilibrium? We need to compare Q to KEQ to answer that question. So we're going to need to write our Q expression. All right, if we look, we've got a gas and a gas, so they're both going to be in our expression. 2 nitrogens, 4 oxygens, 4 oxygens, so it's all balanced. So we get NO2 squared over concentration of N2O4. All right, so there's our expression. All right, now we're going to plug in the given values. All right, so we'll start with 0.55 molar. Square that, divided by 0.12 molar. All right, plug that into our calculator, and we have a Q value here of 2.52. All right, so we check. So in this case, Q does not equal KEQ, so we are not at equilibrium. All right, so then the next question is, if not, in which direction is the reaction progressing? All right, so again, all right, you don't have to do it this way. This is just how I think about it in terms of a line. All right, in this case, here's KEQ. All right, my Q value is actually greater than my KEQ value. So it's up here, close to my products. So Q is greater than KEQ, which means I need to produce more reactants. All right, so the reaction, I almost write the word shift. Shift is not the right word. Progresses towards the reactants. All right, if we think about it in terms of our problem here, oops, sorry, if I can get this number to increase, then I will see a decrease in my Q value, which will get me closer and closer to KEQ. All right, so I'm going to have to make more reactant. And if I make more reactant, then this number is going to have to go down, right? Because I got to get it from somewhere. All right, and then together, those two changes are going to lead to a decrease in that Q value until eventually it matches KEQ and I reach equilibrium. Okay? All right, now, obviously, if I knew the Q value, I could find one of my components, just like I can with KEQ. That's another way to use the Q value, but most often it's this type of problem where you're given all of the concentration to ask to compare it to KEQ and decide whether you're at equilibrium or not. Okay? All right.